So today we'll talk about merge sort, and again, just like on Monday where we talked about sorting as a means to an end to talk about new concepts that we're learning, we're going to talk about merge sort to introduce the concept of recursion. This algorithm uses recursion, and again, merge sort. It's important to know. It's something you should know as a computer scientist. But it is also something you're going to learn about multiple times, many times. You're going to see merge sort at least 2 more times in your career. You'll see it again in 250 when you learn about runtime analysis. And I think they might have shifted this to 250 doing the proof of correctness. But if you don't, in 331, you'll see it again when you learn about proving an algorithm is correct on all inputs. Today, we're going to use it to introduce recursion. The lecture test today doesn't quite match the lecture content. Lecture test 2 you could have done after Wednesday's lecture, so there's not a one-to-one matching of lectures to lecture tests in this learning objective. Just giving you a heads up on that. But lecture test 2, just so we only have one per lecture, I'll introduce here, and you can actually do with today's content. I believe up to lecture task 4, 3.5, maybe. So feel free to try going ahead in the lecture tasks. You should be able to do 3 for sure. And then 4, technically there's a concept in there that we haven't talked about, immutable objects. But lecture task 2, you could have done since Wednesday, so let's formally introduce it. Same structure as your lecture task 1 methods, except now you're computing standard deviation. You already have average and top K, or you're working on them, or you maybe haven't thought about them yet because you're still working on point of sale. That's cool too. But once you get lecture task 1 done, this is the same setup as those, except now you're computing standard deviation instead of average. It really follows the first part of lecture task 1. So compute the standard deviation. You have a type parameter t. You have a list of things of type t. You have a function that takes things of type t and turns them into doubles and outputs doubles. And you want to compute the standard deviation of those doubles. And this setup, a lot of the office hour questions, those of you who did come to talk about genetic algorithms still have this question. I'll keep repeating this and hopefully it'll make sense at some point. I feel like this is one of the things where I don't have like the perfect way to word it, so to say. But you have a list of things of type t. We don't know what t is. Can be different each time this standard deviation method is called. And you have a function that takes a type t and returns a double. So what we want to do is take this list of type t, call this function on each element of this list, and that's going to give us a double for every single element of the list. And then we want to take the standard deviation of those doubles and return that standard deviation. Same thing with the average in LT1. We want to apply that function, and I word this different ways. I say apply the function to all the elements. It's kind of my way of wording it. I don't know if that's more or less confusing than other ways of wording it. But you want to take this list of t's, take this function, call the function on every element of the list. That gives you a double for each element. If there are 10 elements in this list, you have 10 doubles. And that's what you're doing your math on, is those doubles, one for each value of the list. So you never actually care what t is. You just know that you have a function that converts t's to doubles, and then you work with the doubles. Yeah, these different sorts they're important in the sense that they're pretty fundamental to computer science. Like, you should know how these sorts work. In the context of 116, I'm not super concerned that you memorize a specific sorting algorithm. I am concerned that you can use first order functions. So this idea of our sorting methods take a comparator as a first order function and use that to be able to sort based on whatever that comparator does. That I need you to know. The fact that merge sort uses recursion to get the job done, I want you to know recursion and be able to write recursive methods and functions. Whether you can memorize merge sort in if I put on an exam, explain merge sort to me, or even an interview question, explain what merge sort does, I'm not as interested in that. I'm going to ask you things, and the TAs will ask you things like explain recursion, because that's what I care about in the context of 116. You should still know merge sort, if for no other reason at all, because it's a common question that people like to ask in interviews. When you apply for jobs, they might say, explain merge sort to me. It's just one of those things that every computer scientist should know, and employers kind of leverage that to use it as a free interview question without having to think of a more interesting interview question. Explain merge sort to me. Everybody should know that. If you don't know that, we're not going to hire you. It's one of those kind of things. So, if for no other reason, learn it just because it might come up in an interview. But in the context of 116, I care more about your ability to use first-order functions in recursion, which of course are tougher topics anyway. If you can learn first-order functions in recursion, you probably just happen to learn merge sort in passing. So before we talk about merge sort, let's talk a little bit about runtime analysis. This is more of a 191 and 250 and 331 topic, but I will at least introduce it a little bit for some motivation of why even talk about merge sort. Because we just saw merging a sorting algorithm on Monday in selection sort. So why even learn another sorting algorithm, if we already have one? So let's take a look at why. The reason is it's faster. So what do we mean by faster? Well, we're going to measure how fast a method or an algorithm runs based on its asymptotic runtime. First, we're going to use big O notation, or asymptotic notation in general, if you have big omega and big theta, if you want to use those, and little o, and things you'll probably learn in at least one other course. You'll learn all those ones. But we're just going to look at big O. This is the most common one that you're going to see out there in the world. So big O is somewhat a measure of the number of steps that the algorithm takes to arrive at its output, to do its thing, to do whatever it's computing. This can be thought of as the number of additions, subtractions, logical ands, multiplications, the number of steps that it takes, the number of things that it has to do to be able to compute whatever it's computing. We're going to take a measure of that, which is actually an equation. You can count the number of steps that an algorithm is going to take. And we're going to count the number of steps in terms of the size of the input, which we'll name n. And as the input grows, presumably our runtime is going to grow. And we're going to express our runtime, the number of steps taken by this algorithm, in terms of n. So we'll have some equation in terms of n. So maybe I have an algorithm that takes 5 steps for each size of the input. Then I'm going to have a runtime of 5 times n steps. I have some function that's a function of n. That's going to be the total number of steps that the algorithm takes to do its computation. For sorting and for any data structure stuff, for all of 250, n, I shouldn't say all just in case, but at least most of 250, n is going to be the number of elements in the data structure. So for sorting, it's the number of values that we're going to sort, the size of the list, the size of the array, the size of whatever data structure we're sorting. That's going to be our runtime analysis. So for example, I just gave that example, but O of n, that linear 5 times n number of steps taken to do something on a data structure, that's going to have a linear runtime, or O of n runtime, because the amount of steps taken for the algorithm to do its thing grows linearly with the input size n. The big thing with runtime analysis is that we are ignoring all constants, and we're ignoring all lower order terms. We're only going to take the highest order term in the number of steps that are taken. I thought he said BOGO, but it was Big O. Shoot, title is messed up. I'll have to change the title after the stream. I can change it live, but on the VOD it'll be off until I change it. Merge sort and recursion. So it'll update for all of you, but the VOD will still have the wrong label until I change it. Which I'll probably forget, so maybe it won't change. So we only take the highest order growth, the highest growth term, and ignore all constants. So a method or an algorithm with a runtime of O of n, that might take n steps, just flat out n steps total, or it might be 1,000,000 times n steps, or it might be 1,000,000 times n steps plus 1,000,000,000 steps. It could be very huge numbers and actually a very long runtime, but asymptotically, the growth grows linearly as n grows. So this is one of the big things with asymptotic runtime analysis. We ignore all the constants and the lower order terms. Those are both those examples I just said are both O of n or linear runtime. So let's take a look at selection sort and do a very brief. We don't really do runtime analysis in 1.16, so I don't want to spend too much time on it. But a very brief, quick runtime analysis of merge sort. You'll get your fair share of runtime analysis in 250 and 331. If they don't, I don't think any of it made it to 191 yet. I don't think you see it that early. But in 250 and 331. So I'll give you a little taste of it right now. For a selection sort that we saw on Monday, we have a loop that's going to iterate over all the indices of the data structure. Well, I have a data structure of size n. There are going to be exactly n indices. So this outer loop is going to run O of n number of times. In this case, exactly n times, because it's iterating over those indices. I have an inner loop, which is going to run from the current index that we're considering, the one that we're trying to find which element goes here, until the end of the data structure. So this is going to run in the worst case, like for the very first index, this is going to run n times. It has to consider every single index, every single value of every index. And in general, it's going to be n minus I iterations of this inner loop. So we have an outer loop that runs O of n times, and an inner loop that in the worst case runs O of n times. We multiply those together, and we get an O of n squared runtime. This is an n squared runtime algorithm. And I actually have an O of n cubed runtime implementation of the selection sort algorithm. Selection sort is O of n squared. My implementation here is so sloppy, it's so poor, that I actually implemented this as an n cubed algorithm. So you do have to be aware, even when you design beautiful algorithms, you do have to be careful about how you actually implement them in your code. One little mistake and you can be blowing up your runtime like crazy. This is an n cubed runtime because I used apply right here. Apply is a very slow method call. It's actually O of n. It's an O of n runtime method call, which we'll talk about in AO4 when we talk about linked lists. We're going to see why that's an O of n runtime call. This is a very inefficient call. This is intentionally very sloppy because I want to show, I want to motivate linked lists that we're going to learn about later, and we'll see how to get this down to an O of n squared implementation. If you don't like how hand-wavy I was with that runtime analysis, I said the inner loop is worst case O of n, but most of the time, like only one time is it going to be actually n. Most of the time it's going to be less than that. So let's get a little more mathematical. I won't get too mathematical in this course, but let's get a little more mathematical. Since I use apply twice, wouldn't this be n to the fourth? No, because this is additive. So this is going to be O of n plus O of n for the loop times O of n. So these two are multiplied together. So that gets O of n squared for this loop. And this is O of n right here. So we have O of n plus O of n squared. And then we're going to only take the highest order term in the addition. So that's just O of n squared is going to completely, kind of eat that O of n right here. And just get O of n squared for the runtime of each iteration of this loop times O of n for how many times the loop iterates. But when we add runtimes, whatever the highest runtime is, that one's just going to absorb the other runtime. But when we multiply them together, like this, O of n is going to be run for each O of n times. Now we multiply them and get n squared. Multiply, each time you have a loop like that, multiply, get n cubed. But we don't multiply this one. Good question. So with the math, That inner loop is going to run n times for the first index, n minus 1 times for the second index, n minus 2, so on until we get down to 1. Well, you've learned in probably several different math classes, if you sum up the numbers from 1 to n, the equation for that is going to be n times n plus 1 over 2 is usually probably the way you see it, or n squared over 2 plus n over 2, which is a function where the highest order term, we ignore the lower order terms, the highest order term is order n squared, we ignore the constants, and we end up with an O of n squared runtime. So it's a little more thorough analysis, where we're not just saying, well, worst case it's n, so we'll just pretend it's always n. Well, even when we do the math, we do get an n squared term in there. So this is an O of n squared runtime algorithm. My implementation was n cubed, but the algorithm itself is n squared because it can be implemented in an n squared, to be n squared. Series are slowly creeping in all my classes. I don't know about y'all, but don't you get excited about that? Like the fact that when you learned about series and sequences in other classes, that wasn't a complete waste of your time, that actually does creep in other places in your life. Like, would you rather have those classes be a complete waste of time than something that you're never going to use? I don't know. I get excited about that when I see crossover in courses. And I try to point it out, like what I'm doing right here. I try to point that out when we do something that you've seen in another class. So in 115, speaking of another class, in 115 you saw merge sort very, very briefly. I haven't kept up on the 115 to make sure that they're still doing it. I believe they are, but it's like half a lecture. We say, here's merge sort, isn't that cool? And that's about what we do in 115. So let's take a little bit more in-depth look into merge sort and see how merge sort works, and specifically how it gets this O of n log n runtime that in 115 we're just like, trust us, it's faster, and maybe we rattle off a few sentences explaining why. But let's take a look at why it's faster and how it works. And that's what we want to do the rest of this lecture. By the way, have you gotten to DFAs yet in 191? Have you started learning about those? Finite automata? I keep meaning to look at where that is in the 191 schedule. What part of the semester? You skipped all your classes for 191. Well, you might not be the one to ask then. Okay, maybe I'll keep asking that question until the answer is yes. I'm pretty sure I'm quite certain that's part of the 191 curriculum these days. So I was part of the committee that chose what was going in there. So they better be covering that because we're counting on that. But if you get to DFAs or if you look at your syllabus and it's on the schedule, remember the state pattern when you learn about DFAs. That's another big crossover. That's a huge one. Also, recursion that we're learning now. Recursion and induction, proofs by induction. Oh, you're on induction right now? Perfect. When you're looking at recursion, learning recursion here, link that to your understanding of induction. They are pretty much the same thing. It's the same ideas, the same math in the background. We're doing the same stuff. So if you can understand one of these, transfer your knowledge to the other, and you'll be able to understand both of them. And both of them, I think, both are fascinating. But I don't know. I think everything's fascinating. That's why I took this job. But so let's take a look at merge sort. The algorithm. This is the whole algorithm. Well, I shouldn't say the whole algorithm because we're going to spend the rest of the lecture, this many more slides talking about this. But this is a snapshot of the algorithm. So the algorithm, when I say merge sort this list, it's going to do one check first. It's going to say, is the list of size 1? If it is, just return it. It's already sorted. I have a list of size 1. I don't have to do anything to sort this list. There's only one element. It's literally impossible to have a list that's just one single element and have it be out of order. It doesn't even matter. It doesn't even matter what the comparator is. It's one element. It's sorted. Return it. Done. If there's more than one element, we're going to split the list into two halves. We're going to recursively call merge sort, the algorithm itself, on each half. And whatever that returns, it's going to give me two lists. I'm going to assume that those lists are sorted, and then I'm going to merge those two lists together into a single sorted list. You miss conditionals. Conditionals make a big comeback, huge comeback in FP. But by the end of FP, you're going to miss state, banning var. And that's merge sort. That's what merge sort is. Let's spend the rest of the lecture really explaining this. So first, let's do a sample run of merge sort. And of course, right here is the magic. Like, how the hell do we do that? It doesn't seem like anywhere in here that we actually sorted anything. It kind of works like magic in the way that it does this. And that's how recursion feels like, at least at first, when you first see it. It's going to really feel like magic. My goal over these next few lectures is to dispel this magic, ruin your childhood, and show you how this actually works, so you can say, oh, that's not magic, it's just math and computer science and stuff, and conditionals and stuff. That's what a lot of computer science is ruining the magic. So given this input, my childhood. So given this input of a list with 8 elements, this has more than one element in it, of course. So we're going to split this into 2 halves and recursively call the algorithm on each half. For each half, more than one element, split it in half. Each of those has more than one element, split it in half. We keep doing that until we reach what we call our base case, which is a list of size 1. That's the only place where merge sort kind of does something. And where it does something different, I should say, and it's just going to return that list. So merge sort is going to say, ooh, finally, a list of size 1, thank you. Now here, just have it back. It's going to do that with each of these calls. Merge sort is going to look at each of these lists and say, these are size 1, let's just return them. Now, each time we get a return value from merge sort, from one of those recursive calls, we're going to take the 2 lists that were returned. So we have the left half of our original list, the right half of our original list, and we're going to merge those 2 lists into a single list in sorted order. We're going to do that with each of these calls. So this call here made 2 recursive calls. Both of those recursive calls come back, and we're going to merge them into this sorted list. This call here that took 119 made 2 recursive calls. Both of those recursive calls return. Their stack frames are destroyed. We get the return values. And then our task is to sort the list containing 100 with the list containing 19. And we merge those into a single sorted list. Do the same thing here, same thing here. And finally, we get back to this call, which was originally this call right here that took this as its input list. It broke this in half, called merge sort twice recursively, and now we're at the point where both of those recursive calls have returned, and we get the list 1 and 51, and the list 19 and 100. And our task is to merge these 2 lists into this single sorted list with all 4 of those values. On the other side, we do the same thing. Merge these 2 lists that we got from our recursive calls. Merge them into a single list. And then we're at our top level call, the call that had the original list, which split it into 2 halves. Now at this point, we have the return of this recursive call, which is going to give us 1, 19, 51, 100. It successfully sorted those 4 elements. And this, which is going to give 2, 3, 4, 8, which successfully sorted those elements. Now our task is to merge those 2 lists together to get our final output, our completed sorted list. If we have an odd number of elements, it won't look as pretty and symmetric on a slide, so I use the power of 2 for the number of elements. But if we had an odd number, like say this was a list of size 3, it's going to make 2 recursive calls, one recursive call with 2 elements, and one recursive call of 1 element. The recursive call of 1 element is at its base case, it's going to return. The recursive call with 2 elements has to make 2 more recursive calls before getting to the base case. So it'll just keep recursing until all the lists are size 1. It just won't be, a symmetric, a pretty thing to put on a slide. But odd numbers are perfectly fine. And here's merge sort in code. It should still feel like magic. By the way, I usually give a lot of warnings about this, so let me give one. Recursion is a tricky topic. Like, we have a lot of tricky topics in this course, but recursion is one of those that I usually call the slippery. It's a very slippery topic. It's hard to wrap your head around. It's hard to get a real good grasp on without really studying it and thinking about it for a long time. So it's perfectly fine if recursion doesn't completely make sense to you, early on. It might take you another week or so before it even remotely starts making sense, and that's perfectly fine. It's one of those topics that it just takes a while to understand. I feel like I didn't truly grasp recursion. Like, I was able to get through my courses and get through the assignments about recursion. I didn't truly grasp recursion at a really deep level until I was in my PhD studies. Like, that's when recursion finally started making sense to me. Like, that's what's happening. I can start seeing the recursion and, visualizing it and really getting a good feel for how it works. It takes a long time. To get to the point where you can use recursion and get it working, even if you don't fully grasp it, of course, you're expected to get that done by the end of the LO3 checkpoint. But having a firm, deep understanding of it, that takes a long time. Of course, you could say that with anything, I suppose. It takes a long time to really get a deep understanding of anything. So this is the algorithm in the code. If our input is of size 1, and I do less than 2 just to make sure if something weird goes on, it shouldn't happen the way this is implemented, but if something weird goes on where I end up with an empty list, or in a more practical case, if the initial input is the empty list, I don't want to crash on that, so I do less than 2 instead of equal 1. So if the input data is empty list or a list of size 1, just return it. Everything else in this method is in the else, so this will be the last. If this condition is true, this is the last thing the last expression that's evaluated, so that's what's returned. Else, find the midpoint. I'm intentionally using integer division here. So if input data is like 3, for example, I don't want 1.5. So I have an integer, so this is going to be integer division. And if this were 3, for example, this is going to give me 1 as the midpoint. And then I'm going to split the data at that midpoint. This is going to return 2 lists. Maybe I should have done this with the slice method so I'm not throwing something new at you. But split at is going to return 2 values, 2 lists, which are split at this index. I believe the index itself, the value at the index, I believe goes in the right sublet. And I shouldn't even say that because I don't remember 100%. But it's going to split that into two lists by splitting at this index. Now that I have a left and right list, I have those lists split in half, I'm going to recursively call mergesort. Mergesort, this is literally the algorithm, the method that I'm currently in. The method call that's currently on the stack is mergesort, and I'm going to put another call to mergesort on the stack and start over with the left half of the list. And then once that returns, I'm going to start over with the right half and call mergesort again. It's a list or a tuple or a pair. I forget what it's called in Scala. But yeah, I think it technically returns 1 value, but that value is a tuple, the equivalent of a tuple in Scala. But it supports this syntax where you can declare 2 variables in one line and assign each value of the tuple. Doesn't that get stuck at left sort? No. And understanding why it doesn't is part of the magic here that we got to dispel. So it's going to recursively call. Yeah, you're saying won't it get stuck there? So if I'm recursively calling mergesort, I'm just going to keep recursively calling mergesort of left comparator, mergesort of left comparator, mergesort of left comparator. This stops as soon as input data.length is less than 2. That's what we call hitting the base case. We're going to hit this conditional and just return that list. and then this returns, we get left sorted, and then we can recursively call on the right. And then once that gets down to a list of size 1, that starts returning. Once we have left and right sorted, then we can call merge, which we're going to see on a later slide. We're going to see this merge. I like seeing the O's. I love those aha moments. It is big brain stuff. This is why we wouldn't dare show this stuff to you in 115. It would be overwhelming. 116, you're ready for it. It returns a tuple 2? Okay. Good to know. Why is it less than 2 and not less than equal to 2? Because I don't feel like writing the equal. So if you have a list of size 2, you have to do a little bit of work to sort it. You have to find the min and max and then organize them based on that. If I have lists of size 1, then I don't have to worry about it. If the list is size 2, I'm going to split it at that index and then call merge sort on 2 lists of size 1 and let the base case handle it from there. You can do 2. I've seen merge sort implementations less than equal to. Hell, I've even taught it before with less than equal to. But why do more work when the recursion will do the work for you? Yeah, where is the actual sorting happening? Isn't that wild? So let's do a quick runtime analysis on this. I'm gonna call each level of the recursion like this. I'm going to call these levels. I want this one. Where this is level 1, level 2, level 3. For each level of the recursion, if we visualize it as a recursive tree like that, each level of the recursion is going to have 2 to the I lists of size n over 2 to the I. So each time we go down one level of the recursion, we're splitting all the lists in half. So if we're at level I, we're going to have split the initial list in half, I times. So it's n over 2 to the I. And we have 2 to the I of them because we get twice as many lists each time we go down the recursion, and we start with one list. So we have 2 to the I lists of size n over 2 to the I. Our base case is 1, so the recursion is going to end at level I, where n over 2 to the I equals 1, which just so happens to be log n. So after log n levels of the recursion, we're going to reach the base case on an input of size n. Where does it compare one value with another? In the merge method that we're about to see. So we have log n levels to the recursion. Each level has a total of n elements across all these sublists, and each pair of sublists needs to be merged, which we haven't seen yet. And that is where the comparator is going to happen. So if we can merge 2 lists, what we end up with is if we can merge 2 lists in linear time, we're going to have an overall n times log n algorithm. We'll have an n log n algorithm. We have log n levels. If we do linear runtime on each level, total runtime, we're going to have our n log n runtime that we're looking for. So our goal right now is to merge in linear time. So let's see that merge method that we glossed over. For just in case you missed it, this one right here, after we get both left and right sorted, we're going to call merge on those, which are going to merge them into a single sorted list. I didn't show you this, so how does this work? That's something we're going to write. So to merge 2 lists, and of course we can do this in linear time because we do end up getting n log n runtime, we're going to take advantage of these lists already being sorted. If these lists weren't already sorted, we would have to go back to square one and write a whole sorting algorithm. But the fact that these lists are sorted makes us able to merge them in linear time instead of n log n time. We can't do any better than n log n for sorting. It's not possible. So we have to take advantage of the fact that these are just for those of you out there, it's not possible using a comparator to sort. There are ways to sort faster if you're not doing comparison sort. Anyway, we're going to take advantage of the fact that these lists are already sorted, and that's going to let us achieve linear runtime. So what we're going to do is start with a pointer pointing at the beginning of each of the 2 lists, each of the left and right lists. We're going to compare the two values being pointed at by those pointers, and whichever one comes first, we're going to copy that into an output list that we're building, and then advance that pointer. Once a pointer reaches the end of one of the lists, we're going to copy everything from the rest of the list over. So visually, in our example earlier, on our last step of our algorithm, we have the task of merging these two lists of size 4. So we're going to start with a pointer pointing to the first element in each of them. We're going to use our comparator to check which one comes before the other one. So we're going to compare and break ties arbitrarily. I don't have any ties set up in this example, but break ties arbitrarily. And we're going to compare. Call our comparator with 1 and 2, assuming that our comparator is the less than function, using the default integer comparator. We're going to copy 1 to the output and then advance that pointer. Now we're going to say, does 19 come before 2 using our comparator? No. So we're going to take 2, and just the way I said that, we're going to break ties by favoring the right side of the list, even though there are no ties here anyway. So we're going to copy 2 to the output and advance that pointer. 3 comes before 19, copy 3, advance the pointer. 4 comes before 19, copy 4, advance the pointer. 8 comes before 19, copy 8 over and advance the pointer. And the way this works, the way we're able to merge this in linear time, because we're doing one comparison per value that we're copying to the output list, so we get our linear runtime. The way this works is by transitivity. When we compare 8 and 19, 8 comes before 19, and since this list is already sorted, we know that 19 comes before everything that comes after it. So if 8 comes before 19 and 19 comes before these values, by transitivity, 8 comes before all of these values. So we don't have to take 8 and compare it to 19, compare it to 51, compare it to 100, because we know 8 comes before 19, and by transitivity comes before everything else, because this list is sorted. So we reach the end of this list. Once we get to the end of the list, we know that this comes after everything in this list because it came after the last element of that list. So we already know that everything else is in order. So we're just going to copy everything from this list over to the output. Your previous professor made you write merge sort. Writing merge sort can be a good exercise. It's just not one that I'm going to make you do in 116. By the way, yeah, you don't have to write a sorting algorithm. I see that fairly often in this class. Students will come into office hours with their own implementation of merge sort or selection sort. I show these to motivate first order functions, recursion, something else. I thought there was something else in that list. Runtime analysis, I guess, but I don't really care about that in 116. I don't expect you to write your own sorting algorithms, though. Just call dot sorted, dot sort by, dot sort with. Just use those when you need to sort. But writing merge sort isn't too tough. I mean, I showed you half of it already, and here's the other half. The merge half of it. So this is what it looks like in code for merge. We're going to take the two lists that we're merging. We're assuming that these lists are already sorted, and we have our comparator that's going to tell us how to compare two elements of type T so we can get these in the right order, and then return our list of type T in sorted order. So we're going to start with our pointers pointing at index 0. We're going to check. We're going to iterate as long as we haven't reached the end of either list. We're going to compare what's being pointed at the left list, what's being pointed at the right list, and if the left value that's being pointed at comes before the one in the right list, we're going to append to our list that we're building. This is going to be the final output. We're going to append to the output that we're building the value that comes first. The left pointer, we're going to break ties by favoring the right list, append the right, and increment whatever pointer we pulled an element from, and just keep doing that till we reach the end of one of the lists. Once we reach the end of one of the lists, we're going to kind of check, we're just going to do both, but kind of check which list we didn't reach the end of, and copy everything else, everything that's left over. Why do I hear boss music? Boss music is coming when I rewrite this algorithm. That one's going to be a good one. This is horrendously slow, by the way. I'm using apply, which we already know is O of n. So I have an O of n loop and an O of n method inside of it. This is an O of n squared implementation. This is a terrible implementation of merge. The idea is correct, the algorithm's correct, the implementation is terrible. I'm really abusing the way lists work. I'm also using append, which is horribly slow. It's O of n. Appending to the end of a list, at least a Scala list, is terribly slow. Priest says, shake my head, Jesse using var again. You know what? I might have you covered on that one. But I banned var and then I just used it in my damn example. You should be mad at me. You should be mad at me, Priest. You should be really mad. Like, I banned var. You can't use var, but I'm using var. I'm going to use var all the time. Yeah, right. No, so let's rewrite this. Let's get rid of all that inefficiency and get rid of var for the sake of the learning objective. And here, if there's a final boss for this lecture, here it is rewriting merge without var, and incidentally getting rid of the inefficiencies, the inefficient use of list. And to do that, we all but have to use recursion. So I'm going to rewrite this using recursion, get rid of all my vars. You won't see any vars here. But this has the same functionality. This is going to merge two sorted lists. Merge two lists, assuming that they're already sorted, and return the merge in sorted order. So for this is probably a... So what's going... Yeah, let me go through this one. This is a pretty tricky first recursion to explain, but you know what? I'm going to do it anyway. I'll spend some time on this slide. Will I? 6 minutes left. Maybe not a ton of time. So for this, often when you're writing a recursive method, it's helpful to write a helper method where I need this to be the interface that I comply with. I need a merge method that takes two lists and a comparator. But in my recursion, I want to add another variable, something that's going to collect the output list to get the current state of the output, which I call an accumulator here because it's going to be collecting all of the results that I've acquired. I'm going to initialize that through my first call. So my interface, left, right, and comparator is going to defer to my helper, which initializes the accumulator to an empty list. And then I have my recursion, which checks the base case is going to be, is either the left or right empty? If it is, copy everything from the other one. If left is empty, copy the right. If right is empty, copy the left. Where the triple colon is going to combine two lists into a single list. If they're not empty, then I actually have some comparing to do. So I'm going to compare the first element in the left list with the first element of the right list. And depending on which one's bigger, I'm going to copy that element into the output. So if the first element in the left list comes before the first element in the right list, I'm going to prepend the first element in the left list to the accumulator list where I'm collecting all the results. And I'm going to call left.drop1, which is going to remove the first element of the left list and return the rest of the list. I believe I could also do left.tail right here. Now I'm looking at it. Copy the right list unaltered because we didn't copy anything from that list, and then forward the comparator. If the left element doesn't come before the right element, do the same thing but to the right list. Drop one on the right list and prepend the right list. Since I'm prepending instead of appending, that's why I have to reverse up here, because I have these elements in reverse order. I'm just the way that I'm accumulating these values. I'm doing them in reverse order because prepend is much more efficient than append. So I want to prepend to get efficiency, and then I'll reverse when I'm ready to return. And then the return values from this recursion go all the way up, and everything's done. Why the triple colon? So right is a list, and accumulator.reverse is a list. If you want to combine two lists into a single list, triple colon's your answer. No vars for you, priest. So, which gets us to the main point, the main event that we need to talk about is, which we'll continue on Monday, is writing recursive methods. You should all be at the point where you can read a recursive method, even if it takes you a long time. You should be able to trace through mergesort and figure out what it does and convince yourself that it does do what it's supposed to do, even if you don't 100% understand what's going on with it. You should be able to trace through the code. The next trick is writing the recursive methods, and that can get trickier. Can you see the heap? I'll show an example on Monday. I believe I have one planned in that lecture where I'll show you the heap, but I'll show it to you in the debugger. I'm done. I guess not done, but for the most part, I'm done showing you the stack and heap in slides, but I'll show it to you in the debugger. Because with the debugger, you can get infinite examples. You can just run the debugger on your IntelliJ. You can see the heap and stack. So this is my suggested approach on how to write recursive methods. First, assume that every recursive call you make is going to return the correct value. Write your entire method based on that assumption that the recursive calls will be correct. Come up with some base case that has a trivial input and output value, some very simple case, and then if you reach the base case, just return that simple input-output behavior, and then make sure every recursive call gets closer to your base case. You follow these 4 steps, these 4 ingredients, mix them in a pot, mix them in IntelliJ, stir, bake for 20 minutes, and you're going to have a successful recursive algorithm. So let's take a look at this with mergesort. Let's go through the procedure a bit and build this one step at a time. Well, 2 in this first one. But first, we're going to assume our recursive calls are correct and then write our method based on that assumption. So when I write this method, when I write mergesort, I'm going to assume that mergesort, my recursive calls, are going to magically return the correct value. So I'm going to assume that left sorted and right sorted are in fact the left half of this list in sorted order and the right half of this list in sorted order. I'm just going to flat out assume that. I'm just going to assume that the method that I'm currently writing, like assuming this hasn't been written yet, I'm writing this mergesort method. When I write these lines, I'm just going to assume that mergesort is going to be correct. Even though I'm not even done writing the method yet, I'm just going to assume it's correct. It's going to be right, because by the time I'm done with this, it's just going to be right. It's just going to. So I'm going to assume these are right, and then write the rest of my logic, the rest of my method, assuming that my recursive calls are going to be correct. So when I write merge, I'm just going to say, well, let's assume that these are in fact sorted, and I need to merge these 2 sorted lists. So if these calls to merge sort are actually correct, these do return the correct values, then I have a fully functioning correct algorithm. Now we have to add a base case that's some trivial input-output behavior where I know the output without really thinking about it. If the list is length less than 2, I can just return it. It's already sorted. It's either the empty list or a list with 1 element. Either way, it's a trivial input-output. On this input, if this is true, the output is ridiculously easy to compute. I'm just going to return the input. I'm not even going to do anything, not accessing my comparator. I'm doing literally nothing. I'm just returning the input. That's a very simple, trivial input-output behavior, and that's what your base cases should be like. Very simple, trivial behavior. And then writing the recursive calls, whenever you write a recursive call, like how would we decide to split this list in half? How did we decide to even do that? Well, we're going to choose something that's going to satisfy this last bullet. Make sure every recursive call you make gets closer to base case. So if our base case is based on the length of the list being 1, every recursive call I make better reduce the size of the list. So if I have an input of size n, my recursive calls are size roughly n over 2 plus minus 1. These are half the size of the input. If I keep halving the size, I will eventually get to the base case. So we have these 4 ingredients. That means this method just works. At least to that level, by the end of 116, by the end of this learning objective, I expect you to be able to do that, to follow these steps and write successful recursive methods. Even if you don't 100% understand and see what's going on with them. Yeah, just assume it works and then it works. And I think I can skip through these. I pretty much just repeat everything that I said. Choosing a base case, like depending on what you have, if you're working on strings, it's usually the empty string. If you're working on lists, it's usually empty list or list of size 1 like we saw. If it's integers, usually like a 0 or a 1. Those are your base case inputs that are going to have trivial outputs. And I don't think there's anything... and make sure you're always reaching your base case. You don't reach your base case, infinite recursion, Stack Overflow. Stack Overflow is going to be your error and your program crashes. Which brings us back to the lecture.